Hi, nice to meet you all. It's my honor to present our work, an investigation of few-shot learning in spoken term classification, here in Interspeech 2020. I am Yang Bingchen from City University of Hong Kong. The other authors include Tom Kaw from Southern University of Science and Technology, Li Fengshang, Xiao Chen, and Xin Jiang from Huawei North Art Lab, and Qing Li from the Hong Kong Polytechnic University. In recent years, few-shot learning has drawn a lot of attention in the machine learning community, and there are a lot of elegant solutions developed in few-shot learning. So we think it is worth to investigate the feasibility of applying few-shot learning methods to speech tasks. The spoken term classification system aims to recognize the spoken terms in the voice signal. Normally, the spoken terms are predefined, and given plenty of training data, conventional supervised learning algorithms could have solved this problem nicely. Then what about a user-defined scenario, where users can define new spoken terms by themselves, but they can only provide a few audio examples for each new spoken term? It means that the system should be able to recognize the new terms with only a few examples, which is quite challenging. We formulate this problem as a few-shot learning problem, specifically a few-shot classification task. Next, I will introduce two concepts: the few-shot learning problem and the few-shot classification. Few-shot learning problem is a machine learning problem that learns with limited labeled data of target tasks by incorporating external source data, which has a different distribution from target data. Few-shot classification is a few-shot learning task, which is defined as n-way k-shot, as this figure shows. And in each task, there is a support set and a query set. In the support set, there are n classes of labeled examples, and in each class, there are k examples. So we needed to learn a model using the support set and evaluate it in the query set. Right now, most popular solutions of few-shot learning problems use meta-learning. Meta-learning is also known as learning to learn. It aims to make a quick adaptation to new tasks with only a few examples. And there are many elegant solutions in meta-learning, such as matching network, prototypical network, and model-agnostic meta-learning, which is also known as MAML. And in our approach, we take model-agnostic meta-learning to solve our problem. MAML is to train a model which can adapt to any new task using only a few labeled examples. The model is trained on various tasks, also known as meta-tasks or episodes, and it treats the entire task as a training example. The model is forced to face different tasks so that it can get used to adapting to new tasks. MAML has been widely used in few-shot image classification tasks, or few-shot speech classification tasks, or few-shot relation classification tasks in natural language processing. Next, I will introduce the details of MAML. There are two stages of MAML: the meta-learning stage and the fine-tuning stage. In the meta-learning stage, usually we are given an initial model of theta, and in each learning batch, we sample a series of meta tasks. And in each meta task TI, we first compute a loss using the examples from the supporter set, as the equation 1 shows. Then we update the model parameters theta using one or several steps of gradient descent, as equation 2 shows. After that, we use the updated model and compute another loss using the examples from the query set, as the equation 3 shows. And finally, we will combine the losses from the meta tasks in one batch, as equation 4 shows. And you can see that in equation 4, we list two equations because usually one batch contains several meta tasks. So we can combine the losses of different meta tasks, but there can also be only one meta task in one batch. So this first equation is for that situation. And this is a second order gradient optimization. In the fine-tuning stage, each task also consists of a supporter set and a query set. So before evaluation, the model initializer learned in the meta learning stage will be fine-tuned in the supporter set with a few iterations, and then evaluate in the query set. So we introduced the original MAML algorithm. Then in our approach, we extend the few-shot classification problem from n-way k-shot to n plus m-way k-shot. As in most few-shot studies, all the classes are assumed to be new. But in real-life applications, some of the classes are known in advance. So we define an n plus m-way k-shot problem, where m is the number of fixed classes, n is the number of new classes in the target task, and k is the number of examples of each new class. And we extend the original MAML to solve our new problem. We fix the output positions of the fixed classes in the neural network classifier. The fixed classes occur in every meta task in the meta learning stage, but the adaptation of fixed classes is not needed in the fine-tuning stage because they have already been learned in the meta learning stage. And this is the framework of our extended MAML approach for the few-shot spoken term classification. And in the meta learning stage, we sample a number of meta tasks. In each meta task, there is a supporter set and a query set. So our problem here is a 10 plus 2-way k-shot problem. 10 means 10 keywords here, like this. And 2 means 2 fixed classes. And here are the silence and the unknown classes. In the meta learning stage, the meta tasks are randomly sampled from a pool of keywords. And in the fine-tuning stage, in the digits classification task, usually we needed to recognize 10 digits spoken terms here, the algorithm of our approach. Then for our experimental setup, we use the Google Speech Commands dataset, which contains more than 100,000 one-second audio clips from 35 keywords. We formulate 2 10 plus 2-way k-shot tasks using the same setup as the audio recognition tutorial in the official TensorFlow package. And we divide these 35 keywords in, for our need. And our two tasks are digits classification task and commands classification task. So in each task, there are 10 keywords and two fixed terms, the silence and unknown. The digits classification uses digits 0 to 9 as 10 keywords, and commands classification uses 10 keywords as yes, no, up, down, left, right, on, off, stop, or go. And we use the 40-dimensional MFCC features for each spoken term. And our base model is CNN, which contains 4 convolutional blocks. Each block comprises 3 times 3 convolutions and 64 filters. We use 2 baselines. One is the conventional supervised learning approach, which use the test commands, test spoken terms only. And the other baseline is the original memo, which treats the 10 plus 2-way problem as a 12-way problem. And this table 1 is the result on digits classification. The table 2 is the result on commands classification. And from these results, we have 3 observations. The first observation is that the overall accuracy in digit classification is better than in command classification. And this implies that in a user-defined scenario, the system performance will be affected by the keywords users pick. And the second observation is that memo-based approaches perform much better than the conventional supervised learning in a few-shot situation. And the third observation is that our proposed approach outperforms the original memo. And we attribute the improvement to the use of prior information of the fixed classes. We also do another experiment which compare the user-defined scenario and a predefined scenario. Here, the predefined scenario means that we collect quite a lot of labeled examples in this digits classification. And this is the result of predefined scenario. The accuracy reaches near 91%, and compare to our extended memo approach or the supervised learning approach. Here, even we use 100 examples for each class, and there is a performance gap between the user-defined scenario and the predefined scenario. And in the by the way, the predefined scenario use about more than 3,000 labeled examples for each class. And then finally, we will draw a conclusion. In this piece of work, we formulate a user-defined scenario of spoken term classification as a few-shot learning problem. We define an n plus m way k-shot problem, which we believe is a more realistic problem. And we solve this problem by extending the original memo, and we get better result compared to the conventional supervised learning method and the original memo. In the future, as there is a performance gap between a user-defined system and a predefined system, we try to narrow this gap with some other techniques, such as the data augmentation techniques, or explore other meta-learning methods. And that's all for my presentation. And thank you very much for your listening. If you have any questions, you are welcome to see our paper and our code. And if you have any more questions, please feel free to email us. And thank you very much. I wish to see you someday offline. Thank you.